All right, so joins. We're already in week 3. That is crazy. All right, um, learning objectives. So for today, what I'd really like to get through is I would really like for you to be able to understand and be able to identify keys in data sets. Okay, so when you're joining data sets, you have to have keys that you're going to join by. And so I'd like you to be able to have a data set and take a guess at what the key is, and then be able to verify that it is or is not a key. Okay, and we'll talk about how you do that. Understand different types of joins. So primarily there's left, right, inner, and full joins. And then also one-to-one joins and one-to-many joins. Okay, so those are two things are not mutually exclusive. So you typically will have a left join that is either a one-to-one join or a one-to-many join. You don't want to get in a situation where you have a many-to-many join, which we'll talk about also. Understand some common ways that joins fail, and that's primarily by using the wrong type of join or having a many-to-many join. And then understand the difference between mutating and filtering joins. All right, we almost always, when we're talking about joins, talk about mutating joins, which means you're adding new variables to your data set, basically. All right, but there's another type of join that's called a filtering join that can also be really, really powerful and really helpful. Okay, so we'll talk about that a little bit as well. Okay, so that's basically what I just said. Before we really get started, though, I'm going to be talking about mutating joins, which are where we're adding columns to a data set. All right. And one of the common questions I've had is, well, what if I want to add rows to my data set? Okay, that's not technically a join. All right, because there's no key involved, and so you're not actually joining the data sets together. What you're basically doing in that case is just kind of stapling them together. Okay, so this is a quick example of an example where you would want to add rows to a data set. Okay, so I have this little teeny data set here I'm calling G3 that has 3 students in it, SID for student ID, and everybody in it is in grade 3. And then they have these scores, 3 scores with a mean of 200, a standard deviation of 10. All right. Then we have another data set that looks exactly the same, but we have different student IDs, and it's now 4th grade. And then we have some scores. Okay, so here's the grade 3 data set, and here's the grade 4 data set. Notice in these 2 data sets, we have the exact same structure, right? In each of them, they have 3 columns. Those 3 columns are called the same things, and the column types are the same thing. Okay, so this is integer, double, integer, integer, double, integer. Okay, if that's the case, then all you have to do is use this bind rows. Okay, you say bind underscore rows G3, G4, and it will just staple them together just like that. Okay, so the rows just get added, and because the structure is the same, it's super straightforward. All right. There is an optional .id argument. So here I'm dropping the second column from each of them. The second column is the grade, right? So I can drop the second column, and then I wouldn't really have a way of identifying where each row of data came from. All right. But there's this optional .id argument that I can supply, and it will keep like an indicator of what the data set is. Okay. So these first 3 rows came from the first data set. These next 3 rows came from the second data set. And all you do to supply that is you say .id equals, and then in quotes, you put whatever you want that column name to be. So if I said var here, then we would have var there. And that's all it does. Okay? And so that'll help you keep track of where different rows of your data come from. And this is important because oftentimes you will end up in situations like this where you'll have data that's from grade 3, but you don't actually have a column in there that's called grade 3. And you have another data set that's from grade 4, but you don't actually have a column in there that's actually saying it's from grade 4. Okay, so then you can do something like this. And then from there, you can pass that to mutate and say, all right, now I'm going to create a variable called grade. and I'm going to say if else, if data set is equal to 1, then grade, right, is going to be 3. Okay, if data set is 1, then grade is 3. Otherwise, it's 4. Okay, and so then I have now a new column called grade that's 3, 3, 3, 4, 4, 4. Again, in this case, I'm dropping the second column from both of these just to illustrate a way that you might do this if you didn't have that column. Okay, because this is, again, like I said, quite common where you'll have a bunch of different data sets and you want to staple them all together, but you have to have some sort of indicator so you know where those different data sets, like where the data came from, right? So it might be different years of a study, or it might be, in this case, different grades, could be different schools, different school districts, whatever, right? But it's very common that data are split into different files by something, and that something is often meaningful, and sometimes that something is not actually stored as a column in the data set. And so this is a way around that. Does that make sense? Questions on that? Okay. An even better usage, though, of this is if you give the pieces that you're linking together through bind rows names, okay, then it will use those names here instead of just going 1 to n. Okay, so here this data set is grade 3, and I'm calling it G3. Okay, this data set is grade 4, and I'm calling it G4. Then when I use my .id argument, instead of doing 1 and 2 here, I get those names, okay, G3, G4. And so that's nice because, again, with bind rows, you can do this for n data sets, right? So I could say G3, G4, G5, G6, G7, and then at the end, I don't have to do this huge recoding of if 1, then if 2, then if 3, then, or you'd probably use case-when or something like that. But by just supplying the names directly like this, then they'll just be read in like that. Does that make sense? Okay. All right, what if, though, we end up in a situation where we don't have the columns matching exactly, right? So the structure of the data set is almost the same, but it's not exactly the same. So this is an example where I'm, again, just dropping the second column from G4, but I'm keeping it in G3. So G3 has that grade column, but G4 does not, all right? In that case, bind underscore rows will just pad with NAs, all right? So it'll keep this column, and then when it gets to the data set that doesn't have that column, it'll just include missing data there, all right? And so that's a really nice feature, but you have to be careful about it because you can end up in situations where, like, maybe it's called grade in one data set and it's called G in a different data set, or GR in a different data set. And it's going to treat those as different columns, and then you'll end up with these like missingness that shouldn't really be missing, right? And so as much as possible, you want to keep your data sets with the same names and the same type, okay? If we ended up in a situation where grade was numeric in one of them and it was character in the other, then this would actually fail. It would say you need to fix this first, and then we can staple them together, okay? So that's another thing to look out for. Last thing I want to mention before I move on from this is I'm using bind underscore rows here, okay? Bind underscore rows is from dplyr, so it's part of the tidyverse. There are base functions that are very, very similar. The difference is some of these features, like there's not the dot, so rbind is the base one, right? But there's not a .id argument equivalent with rbind. Rbind will also not do this padding of NA, and it will not check the types. Okay, so not checking the types can be helpful because it'll just coerce the types, but it's dangerous because it'll coerce the types. All right, so coercing can be nice if they're easily coercible, but it can also lead to missingness that you're not expecting to have. So bind rows is what I would recommend using because it's safer. And it has a few more features that make it nice. Okay. All right. Last note on this. We'll actually talk about this more next term when we talk about functional programming. But one of the nice things about bind rows is that we can automatically bind a whole bunch of different data sets together. Okay, so that happens with this function per mapdf. Okay, per is the library, and then there's a function in per called mapdf. If you're used to lapply, if you've used lapply at all, which is a loop in R, map is exactly like that. But mapdf takes the result and it binds them all together if it can. Okay, and so mapdf uses bind rows in the background. And so it's really nice because we can do something like this. All right, so here I'm creating a temporary directory, which I'm just calling temp. And then I'm taking just empty cars and I'm splitting it by cylinder. So what this line of code here is doing is it's taking the single data set and then it's splitting it by cylinder. So we have now a different data set for each cylinder. Okay, so we have a data set for 4 cylinders, a data set for 6 cylinders, and a data set for 8 cylinders. Okay, so we have 3 different data sets all stored in a list. Then I'm using this line, which is saying, okay, write out those files to my local directory, column sil 4, sil 6, and sil 8. Okay, so now I have, I can't show you this because it does it all automatically, but I have, this is what this is showing, right? When I say list the files that are in that temporary directory, it says, okay, there are these 3 CSVs, right? Sil 4, sil 6, and sil 8, which I just wrote out. So basically this line takes one data set, splits it into 3 data sets, and then saves those 3 data sets all in this temp directory. Okay, does that make sense? That's all sort of set up for what I'm going to do here. Now we have these 3 different files that are all in this temporary directory, right? And we want to read them in all at once, okay? And so we can use mapdf, which again uses bind rows under the hood. And what we do is we say, okay, mapdf, and then this is saying list all of those files in the temp directory, and then apply rio import. So we're just going to import them, right? I could use read underscore CSV or whatever. Set class to tibble.df, and then I'm including within mapdf, which ends up getting passed to bind rows, .id equals file. Okay, and so now this new empty cars is going to be one single data set again. It's taking those, it's reading in all 3 of those files at once, and then it's creating one file after it binds the rows together. Okay, and so then here it is. I'm saying now select file, mpg, and sil. I'm just doing this so that it's smaller, and you can see it's, you know, looking just like we would expect. All right. If you didn't follow this last part super close, that's fine. This is more stuff that we're going to talk about next term. I just wanted to show a real applied and example of when you would use this a lot, right? This bind rows, where it'll apply it over and over again. Okay, and it does it sort of automatically because we're doing it through a loop. Okay, and then this last part is just deleting that directory and all the files in it. Okay, so that's it for bind rows. Before I move on from that, do you have questions on that, when you would want to do it, why you would want to do it, or how to do it? All right. So now we're moving on to joins. I have this little note here, not to be confused with row binding. Okay, so again, binding rows is adding data like this, right? We have a data set, bind the rows. Joins are, we have a data set like this, and we're going to join it like this. Okay, so we have 2 different data sets, and we're going to join them. So we're adding columns. All right. Before I do this, real quick, how many of you, maybe just give me a thumbs up if you have done any joins before? Either a thumbs up or emoji thumbs up. Okay, so it looks like about half of us. That's great. Okay, so what I'm hoping to do, even if you have done joins before, is that we're going to probably take a deeper look into this than you may have seen in the past. Okay, so start out with keys. A key uniquely defines the rows in a data set. Okay, so if there is a key in a data set, that key will uniquely define the rows of that data set. Okay, to join data sets by keys, that variable has to be in common between both data sets. And importantly, the key does not have to uniquely define rows in both data sets, but it does have to uniquely define rows in at least one of them. Okay, that's the one-to-many join, which we'll talk about more here in a minute. The other thing that can be tricky and is very common is that a key can be more than one variable. Okay, so the simplest case is we think of a key as like student ID, right? Student ID is a key to a data set, and the student ID uniquely represents the rows in the data set. Okay, but what if we have longitudinal data, right? Where we have student ID repeated a bunch of times for every new data collection, every new wave of data collection, right? Then the student ID no longer uniquely defines the rows. Instead, what uniquely defines the rows there is the combination of the student ID and the wave of data collection, okay? The indicator for when the data were collected. There are two primary types of keys. This is a small distinction. This is not the most important thing, but it's just something to sort of be aware of, okay? Primary keys uniquely identify the observations in that data set, okay? And a foreign key uniquely identifies observations in other data sets, okay? So a really common example of this is you might have a primary key like student ID, right? That uniquely defines the rows in a data set. And then you might have in that same data set a school ID, okay? The school ID does not uniquely define the rows in that data set, and it doesn't even work with the primary key to uniquely define the rows because we already have a primary key that uniquely identifies the rows, right? But that would be an indication of a foreign key that you might uniquely identify rows in a school level data set, okay? So maybe you have a data set that has things like teacher staffing, funding, all of that kind of stuff, right? And it's all about different schools. So then each row in that data set is uniquely defined by the school ID, okay? So the school ID in that data set would be the primary key, and the school ID in the data set with students would be a foreign key, okay? But again, this is a small distinction. It's not the most important thing. It's just something I kind of want you to be aware of, all right? All right, so let's do just a little pop quiz sort of thing here. Here's some data, the Eccles-K sample. So it's a sample of the early childhood longitudinal study kindergarten sample. What do you think is the primary key in this data set?
Would it be the child ID because it's possible to have the same teacher and school across the children?
Yes, that would be my guess as well. And I say guess because we can't actually know what the primary key is here unless we test, all right? But just looking at this, just glancing down through it, I would guess there's going to be multiple teacher IDs because a child there might be multiple children that have the same teacher, right? And same thing with school ID. So I'm guessing that child ID is probably going to be the primary key, all right? How do we do this? How do we check? Well, there's a lot of different ways to do it, but one way that's pretty simple is we can take our data set, which I called Eccles back here, right? Early childhood longitudinal study. So we can take Eccles and we can just count child ID, okay? Child ID being the one that we're guessing. And we should see all ones here. There's only one instance of this ID in the data set. There's only one instance of this ID, okay? And all of these n's should be ones, all of them, okay? If there's any that are repeated, then we know that that is not a primary key, or maybe there's an error in our primary key. Because again, the definition of a key is that it uniquely represents the rows of the data set. Okay, so if we count that key, these should all be one. Each ID should occur no more than one time. All right. So how do we then check that more thoroughly? We could print this whole thing out and visually scan it, but that's very error prone and it would take a long time. So instead, we count child ID and then we filter where n is greater than 1. At that point, there should be 0 rows left in that data set. Okay? If there are any rows, then either we have an error in our primary key or that variable is not the primary key. Does that make sense? And again, you have to go back to the definition of a key is it uniquely identifies rows of the data set. So if that key is represented more than one time, then it does not uniquely define the rows, right? Okay, what about here? So this is the income inequality data set. What would you guess is the key here?
Maybe that last column, just because I visually see that it's not repeated.
Income?
Yeah.
Yeah, so income could...
But it doesn't have to be.
Yeah, it doesn't have to be. Income is actually basically our outcome in this data set. It's the thing we're interested in modeling or exploring or whatever. So it's not going to be our key because it might, it's possible that it could uniquely identify the rows, but if it did, it would just be by chance, right? It's not something that's planful and that is purposeful.
Can the ID column, can that uniquely identify the first column ID, well, where a column? Or
the row numbers?
Yeah. Can row numbers?
Yeah, so the row numbers will always uniquely define the data set, the rows of the data set, but they're usually not very helpful in terms of keys for joining data sets, right? Because they don't link to anything else. And if we switch the order of things, then those row names may get reset, right?
Those were set with ID, then could they become a key?
Say that one more time.
If they were set with ID, like you showed in row bind, if they were set with ID, could they become a key?
Yeah, so I'll actually show this in a little bit. There's a row names to ID, I think is the function that will take the row names and put them as an actual variable in your data set. And then you can use that as the ID. So that would be a case where we would have an implicit ID, okay? But there is actually, of these columns, there is actually a key of the ones that are represented, not including the row names. Any other ideas?
Would it be a combination of columns?
Yes.
Like percentile and year or something?
Yes, that's exactly right. Okay, so here, year is obviously repeated. Percentile is obviously repeated, but percentiles within a year are not going to repeat, right? The percentiles within 1 year don't repeat. And so every time we switch years, we start over the percentiles. And so the combination of year and percentile together will uniquely define rows, okay? So again, 1947 doesn't uniquely define rows, but 1947 and the 20th percentile will uniquely define this row, right? Whereas 1948 and the 20th percentile uniquely define this row, right? So this is an example where we have multiple variables representing a key, okay? And again, we can verify that by taking our data set, counting each of those two variables, year and percentile, and then filtering where n is greater than 1. And we should end up with a data set that has 0 rows as we do. Okay? Questions?
Is there any benefit at all to doing it, to having this like double row? It seems inefficient to me.
Yes, there are. Because what you are often doing is, this will happen a lot if you're working with relational databases, is you have, you might have 30 different data sets, right? And so you have to be able to efficiently link all of those different data sets. And if every data set has its own unique key for every single row, then it can just get really complicated, right? Whereas here you would probably have, different data sets for each year, and then each of those would have percentiles, and you just bind the rows, and then you're done. Does that make sense? So it's,
yeah, I guess I just feel like I would have done like a mutate call and made like a list of like ID numbers 1 through whatever, and then, but I guess that is manual, so less efficient. But yeah.
No, I mean that's fine in this case. But for example, you might end up with like a new data set that has that already has year and percentile in it, and you want to join that with this one, right? So you would have to create a new key in this one, and then make sure that key is the same thing in that new data set that you're creating, and then join them, which is more error prone than just using the keys that already exist.
Okay. All right. That makes sense.
Yeah. All right. Okay. Sometimes there is no key, and this is what Brock was mentioning there, where we have to use the row number basically as the implicit ID. And in this case, this is way less than ideal, right? And so here, if you want to join the data set with anything else, you're in bad shape, basically, right? You can do it if there's a unique key in the other one that will link to something in this data set. But if there's no unique key in the other data set, and there's no unique key in this data set, then you're just stuck. There's not really any way you can systematically join these data sets. And so, but regardless, even if that's the case, I would recommend from the start creating a key in that data set, okay, which is basically what Chris was just suggesting. Okay, so here's an example. This is the NYC Flights 13 package, which has a bunch of different tables in it. Okay, this flights data set does not have a key. Okay, any combination of these things will still not uniquely define the rows. So here I'm counting year, month, day, flight, and tail number. And if I filter for n greater than 1, we still get 11 rows. Okay, so there's no key here. So what I can do is create a key. So as I mentioned, if you're using the row number, that's called an implicit key. And a lot of this vocabulary, by the way, is not super important, but I'm just saying it for background for you, okay? But if you create a key from that row ID, then that's called a surrogate key, okay? And so I would recommend you always do this if there's no key, because then when you start to sort and different things, it's just a way for you to keep track of the different rows, all right? So here I have flights, and I just use this function row ID to column. You can actually pass an additional argument to that for what you want that column to be called. If you don't supply an argument, as I have here, I've just left it empty, right? If that is the case, then it will just come up as row ID, all right? But I could just put in quotes here, like, I could put like whatever, made up key or surrogate or whatever, and then that's what would show up here instead of row ID, okay? And so now I have a key moving forward. That key is not going to be as useful as others because I can't use it to join with other data sets, but it will at least help me keep track of things as I'm, rearranging the data set, basically. And sometimes it is totally necessary if you're moving, say, from long to wide. You might have to have that row ID to make that transformation happen. okay? All right, so all we've done so far is talked about keys. We haven't even talked about actually joining the data set yet. So what we're going to talk about first are called mutating joins, okay? And mutating joins are adding new columns to the data set. So the easiest way to think of this with the vocabulary, right, is that in the tidyverse, we use the function mutate to add new variables or to create new variables in the data set, right? So a mutating join works the same way. We're adding new variables to a data set through a join, okay? So when you use mutate, you're creating a new column. When you're doing a mutating join, you're adding new columns. That make sense? So you have two tables, two data sets that you're joining based on a common key, okay? And again, that key must be a primary key in at least one of the data sets, meaning the key must uniquely identify rows in at least one of the two data sets, okay? There are four types of joins, types of joins generally, all right? A left join, a right join, an inner join, and a full join, okay? And these are really important to keep straight because the type of join that you're doing might, well, in some cases will not matter at all, but in most cases is going to change the result, the output that you end up with, all right? And if you use the wrong type, you might end up with an error. And the most problematic is you end up with like half the data that you expected to have, okay? So a left join means you have a left data set and a right data set, and you join them together and you keep all of the data in the left data set. But if there's anything that's not matching, like say with the keys, right? They come together like this, these two don't match, they go away, all right? And you keep everything in the left data set. A right join is the exact opposite. So we have this same thing, right? These two don't match, these two don't match. But with a right join, these would go away, right? And these stay, okay? An inner join means these come together and then only those that don't match go away. So now we're more like this, okay? And then a full join is you just keep everything, all right? I've practiced my hand symbols a lot, if you couldn't tell. Pretty proud of them. All right.
I think it was backwards. I think your left and right were backwards.
Well, that's just because I'm on the camera that flips everything. So
Kidding.
I need to reverse it when I do it, I guess. But we'll see more examples of these. All right. So real quick, I mentioned this right at the top, but if the two data sets, so like if you have a key and that key uniquely defines the rows in both data sets and you have the same keys represented in both of them, then everything, they're all the same, right? So if all 5 of these go together, it doesn't matter if we do a left, a right, an inner, or a full. If they all match, then it's going to result in the exact same output no matter what, okay? But if we have any instances where they are not the same, then each of these different joins will result in a different output, okay? You can also use joins to recode variables. This is actually a fairly common use case for me because I often end up in situations like this where I have things like disability codes, okay? And so there's a whole bunch of them. And I'd probably use case when if I were going to do this more manually, right? But what I have is something that looks like this, right? So here's all the disability codes. 0, 10, 20, 40, 43. And these are they all mean something very different, right? But just those numbers probably don't mean that much to me, right? So I put them all in a data set and I end up with something like this. So like, let's just imagine this is like a simulated data set, right? So this is what I've done here is I've said sample 200 times from disability code, replace equals true. So I'm just sampling 200 different disabilities, and then I'm creating a score, 200 scores. Okay, so when I use head here, I'm just showing you the first 6 rows of this data set, but these are 6 theoretical students, right? 0 means no disability, and then all these other ones are different types of disabilities, okay? So I have this data set, and that's cool, but these are the actual codes. These are what these things mean, all right? So 0 means not applicable, so there's no disability, and then the rest of these are different disabilities that we might care about, okay? So one method would be to use case when, which I mentioned before, okay? So if I wanted to recode each of these to mean one of these, right, to give me more information, this is one way I could do it. Use case when, and I'd say when discode is equal to 10, then intellectual disability. When discode is equal to 20, then hearing impairment, on and on and on, right? That would work. And then we'll say true is not applicable. So I'm not including 0 in here. Anytime it's 0, it will be not applicable, right? That's one method, and there's nothing wrong with that method. But this is a different method, all right? I create a new data set that has just these codes and then the definition of those codes. One of the reasons that this is a nice thing to do is I'm showing you how to create the data set in R, right? But you could actually do this in an Excel file and then just read in the Excel file, right? Or you could have somebody else do it for you, right? Maybe you have a research assistant or something who's working with you on your team, and you can say, okay, here's all these codes, put them into a file, and then give it to me, and then you can read in the file. All right. So now I have this one data set that looks like this. Okay. Here's these different codes. Here's what those disabilities correspond to. Okay. Again, back here with this data set has 200 rows. All right. Whereas this data set has only these 14 rows, one for each disability type. Okay. But because I have this discode, I can join by that. Okay, so I'm going to say left join disability table, all right, which is my one with 200, with the disability code table, okay, which is this one with 14. And what I end up with is all 200 rows, but now I have this new column called disability that has all of those disabilities. Okay, does that make sense? So this is basically just an alternative to using that case when. And it's particularly nice. In this example, right, we had 14 different disabilities, but sometimes you might have like really intense recoding that you have to do that is maybe like, 100 different things or whatever. And so that's an example where just opening an Excel file and just doing it there and then reading in that file and then just joining it with your data set is probably going to be more efficient. Okay. All right. This is also an example, though, where this is a one-to-many join, which we'll talk about more. But this is also an example where we have the key is disability code, right? We have all 14 of them here, and we have all 14 of them here, here, right? So the key, all levels of the key are represented in both data sets. What if we have imperfect key match? All right. This is where left, right, inner, full is going to matter a lot more. Okay, so this is a super simple example, but here we have a table for gender and a table for SPED. Okay, and gender looks like this: key 1, 2, 3, and then an indicator for whether the person was male, identified as male, and we have 0, 1, 0. Okay, over here we have SPED, and our key goes 1, 2, 4. All right, so this would be like a student ID or whatever. So we have 1, 2, 3 here and 1, 2, 4 here. And then SPED indicator goes 0, 1, 0. All right, we want to join these data sets, but our key does not match perfectly, right? So again, this is where left, right, inner, full is going to matter a lot. Okay, so just for a second, I'm going to pause for just a second. Look at this data set. We're going to treat gender as the left data set, SPED as the right data set. I want you to picture in your mind what you would expect the outcome to be with a left join. Okay? Let me just give you a few seconds to do that. And then give me either a thumbs up or a thumbs up emoji when you feel like you're ready, you feel like you know what it's going to be. All right, here we go. Left join is going to look like this. Is that what you were expecting? So we have key 1, 2, 3, right? We had gender as our left one, so it's going to keep all of these. Male is obviously just going to be 0, 1, 0, exactly what it is. But then for sped, we're going to get 0, 1 on 1, 2 because those match, right? But for 3, key 3, that's not represented in sped. So we have no idea whether this person whose key is 3 was in sped or not. So it ends up being NA. Okay? All right. What about a right join? Think about the same thing. And I'll go back again. Give me a thumbs up when you feel like you know what a right join would look like. All right. Here we go. Left join, right join, looks like that. Okay. So 1, 2, 4 now, because we have the right join. And for male, it's going to go 0, 1, but then we don't know whether that person identified as male or not. Okay, and then we have all of them for sped because we know that for the right data set. Okay, but notice person 3 is no longer represented in this data set at all, whereas person 4 was never represented in this data set. Okay. What about an inner join? Think about that one for a second. When you feel good, give me a thumbs up again. All right. Inner join looks like that. Okay. So we have 1 and 2. Those match for both data sets. That's it. Okay. Person 3 is not in both data sets, and person 4 is not in both data sets. Only people 1 and 2 are represented in both data sets. So those 2 stay, and person 3 and 4 drop. Okay. All right. Last one, full join. This one's a little more tricky, but I will give you another second. Try to predict what a full join is going to look like with these data sets. And then give me a thumbs up when you're ready. Okay, here we go. Full join looks like that. Okay, so now we have everybody 1, 2, 3, 4, and we just have NA for male for person 4 and NA for sped for person 3. Okay, so in this case, it seems like, oh, okay, full join seems like it's the best, right? And maybe it is, maybe it's not. It depends on your purpose. But you have to, I would be careful about full joins because it can make your data sets blow up, and you have 18 bazillion rows and you have 15 bazillion missing rows. So you want to be careful about throwing away data. You also want to be careful about bringing in data that's not useful or helpful for you. Okay, so my general recommendation is start with a data set that you have that is important to you, and that's like your primary data set, right? Then from there, just use left join to add data to that data set. Okay, That's my general recommendation. It's not always going to work, but in my experience, it works probably 80% of the time, where you're going to have one data set that is like your main data set, and then you're just adding data to that data set through left joins. Okay, does that make sense? All right, I have just a few more examples here. This is, and actually that previous example also is from the R for Data Science book. So this is just showing visually what we just walked through, right? So this is an inner join where 2 matches and 1 match, so they're there, and we end up with this. Left join, 1, 2, 3 stays, but then 3 doesn't match over here, so it becomes NA, right? Right join, same thing, 1, 2, 4, NA, so now we end up with NA there. And then the full join, 1, 2, 4 goes to NA and 3 goes to NA, and we end up with this. Okay. Last one I want to show you are some animations by a guy named Garrick Aiden-Bowie, who actually just recently took a job with our studio. These can all be found here. So it's a link to the actual code to produce these. These were made with GG Animate, and I think they're quite nice. Okay, so these are just visuals of exactly the same data sets that we just looked at, but what happens when they join. Okay, so there's the left join. Everything from the left data set is staying, and anything that doesn't match with the left data set drops away. Right? Right join is going to be basically the same side, except now the preference is to the right side. So everything on the right data set stays, and anything that doesn't match with the right data set drops. Okay. Inner join, anything that doesn't match in both data sets drop. So only those that match in both data sets stay. And then full join is a little more complicated, but we're going to keep everything basically. And if it doesn't match, it'll just be padded with NAs. Okay, so we're keeping all the keys, right? So all the students or all the whatever. And if they don't have data on those other columns, then we just have NAs. Okay, before I move on from that, are there any questions on the differences between those 4 types of joins? If you've done quite a bit of joining in the past, this probably feels pretty natural. If not, this probably feels not very natural. And it probably feels like I have no idea when I would want to use one type of join versus another. And so that's where I mentioned I would start out by saying, this is my primary data set, and I'm going to use left joins to just add data to it. Okay. But in some situations, that's not always going to be best. And I think as you get more experience and you're doing more and more joins, you'll see that more often. Okay. And it'll be obvious to you because you'll say, I don't want to drop data from either of these, so I need to do a full join. Or if the data are not in both data sets, then I don't care and they can drop, right? Then you'll do an inner join, that sort of thing. All right, so what if the key is not unique? So in this example, right, we have 1, 2, 2, 1, and 1, 2. This is not a problem at all, so long as the key is unique in one of the data sets. All right, so the key is unique in this data set, and it's not unique here. So here we go 1 matches here, and 1 matches there, and then 2 matches for both of these, and we end up with something that looks like this. Okay. That's exactly the situation that I showed you before when I was recoding disability, right? The disability codes were unique in the disability code table that had only 14 rows. They were not unique in the other one though, right? We had a sample of 200 made up students, and the student ID was unique, but the disability code wasn't. But because it was unique in that table that had only 14 rows, we can match them and it it's fine, right? So this is an animation of the one-to-many join, right? So we have 1, 2, 4, 2, and so that 2 just basically gets duplicated over here, and then we have x2, x2, and y2 and y5, right? So that's not a problem. And this is really common, and I would say actually, well, I don't want to say most, but it's very common that you will do a one-to-many join. Here's an example of another example of a one-to-many join. Okay, so here I have a data set where student ID uniquely represents the rows of this data set, right? But this data set also has a school ID variable. Okay, so this is an example where I have a primary key, which is SID, and a foreign key, which is school ID. Okay, and then we have some scores. Okay, so this school ID is not really helpful for this data set. I mean, it might give me a little bit more information about where these kids came from, but it's not really doing much for me because this score does not correspond to a school. It corresponds to a student within a school. Okay. Then I might also have a school level data set that looks like this, right? So now school ID in this data set does uniquely represent the rows, right? So we have the school ID 1, 2, 3, and then we have student teacher ratio and per pupil spending. Okay, so 2 different variables about these 3 schools. All right, this is a really common example where we would want to do a one-to-many join because maybe we want to use that school level information to predict student level scores. Okay, so all we do is we say left join stu, our student level data set, with school. All right, and then 1, 2, that's student ID. We have 1, 1, 1, 1, 1, 2, 2, 3, 3, 3, right? So these are the different schools, and you can see student teacher ratio just repeats for all of these because it's the same school, right? So it makes sense. It's a school level variable. So once we get to a new school, then the data change, right? And so that's again an example where we would be using a school level variable to potentially predict student level scores, or in this case, multiple school level variables. All right, what if the key is not unique to either table? This is generally an error, okay? There might be cases where it's not, but in my experience anyway, that's super rare. It's almost always this is going to be an error. And what you end up with is the Cartesian product of these. So 1 matches here, that's great, but 2 is not uniquely represented in either of these, all right? So what happens is this 2 here, x2, matches with y2 and y3, right? And this 2 here for x3 also matches with y2 and y3, okay? And so then we end up with something that looks like this. We had 1, 2, 2, 3, 1, 2, 2, 3, and we end up with 1, 2, 2, 2, 2, 3, all right? And what can end up happening with this is you have 2 data sets, right? You join them. The key is not unique in either data set. And so you start out with, say, 100 rows in one data set and 200 rows in a different data set, and you end up with a data set that has like 4,000 rows or something like that, right? And so if you have that sort of situation, then that's a real red flag that you've probably made an error on your joins. Okay, and so then you would want to go back and check those keys like we were doing earlier, where you would count the instances of the key and then filter for n is greater than 1 and make sure that it's uniquely defined in at least one of them. And if you end up with that situation, you probably will have neither of them are unique. Okay, so here's an example, right? I have seasonal means for the school IDs. All right, so here's school 111, 222, 333. So we have fall, winter, spring scores for each of these 3 schools. All right, when I join them, the student level data file where school was represented with this seasonal means, we end up with something that looks like this, right? So here's student 1, fall, winter, spring, 0.34, and you can see that's just copied again and again and again, right? And so that's generally going to be an error. This actually, I probably shouldn't have done exactly this example, because this is one where you could potentially argue that it's not an error, because you want to have those 3 time points for a school for each student. But I would argue there's a better way to do it, which I'll show you here in a second. So generally, this is going to be an error. So how do we fix this? I can't tell you. I mean, I can tell you that you have to have one unique key, but the ways in which this will end up manifesting are so varied, right? They're almost always different and unique to every data set. So you have to have at least one key, one unique key. And if you don't, you need to figure out a way to get that, right? And that's about as much as I can tell you, because it's going to be different in every single case, all right? So in this case, the most straightforward way to do this, and a very common way to do this, is to move the data set to wide first, okay? So I have that seasonal means, and I'm going to say the names are from season, the values are from mean, and I end up with a data set that looks like this, okay? So now I have columns for fall, winter, spring, right? And then I have school ID 1, 2, 3. So now school ID is uniquely defined in this data set. And when we join them, now we're back to only having our 9 rows, right? And we have new columns for fall, winter, and spring. Does that make sense? If you wanted to, at this point, you could move back, back to long. So you could say, okay, now we have this, and now we're going to move it long again. And that would actually put you exactly where we were before, which is why I was saying this is potentially one case where you could argue it might make some sense. I would still, though, actually argue for this approach, where you move it to wide, join it, and then move it to long, versus doing the join where you're ending up with the Cartesian product, because this is more planful, it's more organized, and it's more clear, like this was purposeful. We started here, we made the join worked, we didn't have any, we had exactly what we expect, and then we're moving to long from there. And it's like, I would still actually argue that this is kind of a weird, funky data set, because now you have like long data for schools and long data for students. So it's like kind of weird. And you have, well, rather, sorry, you have one score for a student, right? But you have long data for the school. So the scores here are changing for the school, but not for the student, which is kind of the opposite of what you would normally have, right? You would normally have the score changing for the student, but not the school. Okay. All right. So
Daniel, I have a question.
Yep.
So we should not combine 2 data sets that are in a long format ever. So we should like transform them to a wide format first.
no, so that's not quite what I was trying to say. What I'm trying to say is that you should always have unique keys. Okay, so that in at least one of the data sets. So you could have 2 data sets that are long, but one variable or the combination of multiple variables should represent the key in at least one of those data sets. Does that make sense?
Yeah.
Yeah. So as long as that is the case, then I think you're safe and you're fine. Again, the reason I'm arguing in this case to move it to wide, then do the join, then if you wanted to go long again to do it that way, is because then it's very clear this was purposeful. These are the decisions that I'm making along the way. All right. But what I probably should have done to illustrate this better is had student scores that were varying by fall, winter, spring, and then schools that are varying by fall, winter, spring, because then it would be very clear that we would have 9 rows for every one student, right? So if we had 3 scores for a student and 3 scores for the school, and then we tried to join them, we'd end up with 9 rows for every student, where the school mean would vary for every seasonal score, right? And so then that's clearly an error, and that's not what you want at all. This one, like I said, you could argue this is is okay. It's still sort of weird, but it might be what you want. But even if this is the ultimate outcome that you would want, I would still argue for doing it in a way where you're making joins that are not ending up with the Cartesian product of those keys. All right. So this approach, like I'm saying, is more systematic, more predictable, and ultimately less error prone. So whenever you're doing joins, this is like the take-home message. Whenever you're doing joins, you should be checking your keys first, making sure that the key is uniquely identifying the rows in at least one of the two data sets. Okay. Then once you have that verified, you need to figure out what type of join you want. And again, like I said, for me anyway, about 80% of the time, that's going to be a left join. Okay. Questions? Other questions? All right. So another example, often you want to add summary info to your data set. You can do this really easily straight through piping. Okay, so here's the Eccles K data again, same data we were using before. And let's say we want to compute group means. Okay, so I'm going to take the Eccles K data set, I'm going to group by school ID, and then I'm going to summarize to say the school pre-math score, right? So the pre-test math score for each school. Okay, now I have this data set, and I might want to join that back with my full Eccles K data set like this. So then we have student level data, and we have summary data for the school. So again, another like really common way that I would do this typically is like maybe I want demographic information for the school. So like the percentage of kids who are eligible for free or reduced price lunch, right? Because that's an indicator of like economics, and that's going to be an important predictor of students' scores. If 100% of the kids are eligible for free and reduced lunch, that's going to be a much different school than a school that has 10%, right? So I would probably first calculate these means, or in this case, or proportions in the case I was just mentioning. And then you can just join it with your data set. One of the things that is nice is if you're piping like this, right? Once I pipe down to this point, this is my data set, right? That's it. This is the data set I have. So then if I'm doing a left join with Eccles, I'm going to keep all of the school IDs, and then I'm going to add all of the other rows from, or all of the other columns from the Eccles data set, right? And then I'm just selecting here just to keep space. But basically what we've done here is in one pipeline, we have created summary data, and then we've joined it back with our original data set, okay? This example used to be really nice, but to illustrate this concept, but the tidyverse is always ever expanding and making things easier for you. So now actually this is more complicated than it needs to be. You can actually just group by school ID and then say mutate to calculate the mean of a school, and that would be easier and would work as well. All right, so this is really not that important, but it's just another example of what you can do. This stuff is important, okay? Default join behavior. By default, whenever you're joining, you notice right back here on all of these joins I've done all the way through here, I have not ever, like here, right? I'm not ever telling it what the keys are, what it's going to join by. It's just figuring it out on its own. And that's because I am consistently, throughout the slides up to this point, using the default behavior. Okay, the default behavior with the dplyr join functions is to search through the column names in each data set and join by all the columns that have the same name, all of them, okay? So by default, it's going to use as the key all of the columns in each data set that are in common, okay? And so that's a good, reasonable default, I would argue, because the more columns that you include, the more likely you are to end up with a unique key right? So for example, if we have student ID and school ID, adding school ID may not add anything in terms of uniquely identifying rows because student ID might already do that. But if you join by both of them, it's not going to hurt anything because it's already uniquely defined by the one, and including a second column will only increase the likelihood that you found a unique key. Okay, so here we are, right? We've got two different flights data sets, flights and weather. And when I say join by these two, it will, I've suppressed this message, but it's going to default to joining by all of them, and it'll give you this message telling you the columns it joined by. Okay, so in this case, it joined by all the ones that were in common. So year, month, day, hour, origin. Okay. Sometimes we want to only join by some variables. And this is really important because sometimes you end up with data sets that have the same column name in two different data sets, but they mean different things. Okay, so we have the flights 2 data set and planes. Okay, and in this case, we would not want to join by year because in the planes data set, right, year is the year that there was some maintenance on the plane. All right. In the flights 2 data set, which is this one, year is the year that the flight took place, right? So year in this data set means a totally different thing than year in this data set. So we don't want to include year in our join because that'll mess everything up, right? So instead, we just say by, and then we specify the variable that we want to join by. And if you want to have multiple variables, you can just use C and then pass all of those variables with commas between them. All right. Notice, though, that now I have year.x. So this is year from the flights 2 data set, and year.y, which is year from the planes data set. Okay. You can change that instead of being .x and .y by passing additional arguments to left join. I'm not sure what it is off the top of my head, but you could look at the documentation and figure that out. The other thing that is probably more common is you have mismatched names, okay? At least more common in my experience in the work that I do. Okay, so here is an example where we have school, and I'm changing the name to be school_ID instead of SCID like it was before. Okay, so now I have these two data sets that I want to join where it's called school_ID in this data set and it's called SCID in this data set. But those actually are the same thing. They're just named different. All right. So if I use the default behavior, it's not going to be able to find anything. It's going to say there's no variables that are in common between these two data sets. So what do you want me to do? Right. And so what we can do is we can specify by again, and then we use this C and we say school ID on the left data set is equal to school_ID in the right data set. Okay. So it's saying this variable on the left data set is the same as this variable on the right data set. And then it'll say, okay, I'll use those two variables and treat them as if they're the same, and it'll join by them. Okay, so that's it for mutating joins. We have about 5 more minutes. I'm going to talk about filtering joins really quick, okay? The main filtering joins that we'll use are semi-join and anti-join, okay? Semi-join works exactly like left join or inner join. The difference is it won't actually add the columns for you, okay? So again, if you have, I'll do it this way. If you have a left data set and you're joining a right data set like this, right? Then if you're using a semi-join, then these ones will go away, all right? And these won't actually be added either. So all you're doing is you're saying, okay, here's a data set that has some cases I want, and here's my primary data set, and I'm going to remove these rows that don't match with this other data set. Okay, so here's an example where this is probably a not very good example, but it was just what I came up with. Identifying outliers, right, in a really poor way. So I'm saying, okay, 3 times the standard deviation of TM1's scale. All right, so I'm calculating all these averages, and I've calculated some cut here that I'm saying if it's above that point, then we're going to classify them as outliers. Then I'm going to filter where average pre-math is greater than that cut. Okay, and I end up with these 3 cases. Okay, so back here, I have 707 cases. That's after summarizing, though. Let's see. I don't have it anywhere. Real quick. I think I might have it here. Okay, 984 cases. All right, 984 cases. After I do this summarizing, I end up with these 3 cases that are where the average pre-math is higher than this cut I've established. All right. Now I'm going to use semi-join to basically just add all of the other variables back to this. Okay. So because I have Eccles, I'm going to say extremely high. So I'm taking the Eccles data set and I'm keeping only those in the Eccles data set that match with this extremely high. Okay. So I have the Eccles data set and I'm saying, give me only those variables. Notice I end up with 4 rows here. Why is that? Because one of this is by teacher ID. Okay. And this teacher is represented twice. Okay. So this is an example where I'm maybe looking into these variables, like these ones are outliers, and I want to just filter my data set to include only these outliers. Okay, so I first get a data set that has only those outliers, and then I use semi-join with my original data set to say, okay, now these are the rows that are only for those outliers, and then I can inspect them more. All right. Anti-join does the exact opposite, and in this case is probably the one that we would want to use, where we are saying, okay, here's our outliers, and we want to remove them from our data set. Okay, so we're not adding new columns, we're just trying to filter our data set based on the way that they match. Okay, so I have in row and Eccles is 984. I use anti-join with Eccles, and I end up with 980. So those 4 cases that we found before that we maybe inspected after we looked at them with semi-join, we're now removing with anti-join. Does that make sense? So again, the reason that we would do this is we've done this summary statistics stuff to end up with a data set that has only these specific cases we're interested in. And then we want to maybe inspect these cases more. This is like diagnostic sort of stuff, right? And so then we use semi-join with our original data set to get all of the columns for just those rows that meet some criteria. And then eventually maybe we say, okay, we want to remove these, then we use anti-join. So why is this beneficial? You could, of course, probably mimic the same sort of behavior with filter. Sometimes, though, that's going to result in super complicated, really long code to get to these specific cases. And it's probably going to be more natural to just do some interactive work where you're identifying these cases. And then once you identify them, you can use semi-join or anti-join to remove them or inspect them closer. All right. One more quick example of that. This one's probably a little more realistic. I mean, I think the other one actually is fairly realistic, but this one is one I use all the time. Okay, so here's an example. I'm going to go through this super quick because we only have like 1 more minute. But we have words, right? So we move this like this. We have the book and we have a word, and then we want to count the words, right? So this is something that we would do if we're doing text analysis sort of stuff. How often do specific words occur in different books? All right. So I'm counting word. I'm going to sort equals true. And then I'm just creating a plot, and it looks like this. The, to, and, of, her. This is not very useful, right? That tells me nothing, right? But what I can do is there are data sets out there full of things called stop words. Okay, stop words are just common words like and, of, the, is, etc. Okay, and so what I can do is I can use anti-join with the stop words. Okay, so I have all of my words, and then I'm going to use anti-join with the stop words to remove all of the instances of those stop words. Then when I produce my plot, I get something like this: Miss Time, Fanny, Dear, Lady, Sir, Day, Emma. Okay, it's much more useful, much more informative. And it's particularly that way when you look at it by book, because now you can very quickly sort of pick out themes across the different books. All right, so that's a very clear example of where anti-join is really, really helpful. Okay, because can you imagine trying to write a filtering, like filter where word does not equal where word does not equal and, where word does not equal, right? It would go on forever, but using anti-join is just automatic. Okay. All right, so homework 1 is assigned today, but it's not due for 2 weeks. So take a look at it, and then if you have questions, let me know. We'll talk about visual perception next time. In the homework, you will be asked to do some joins, and just be careful about keys, all right? It's likely to be tricky.